Let's continue with another example using the disk method. Golly, disk method. Anyway, so if I have y equals e to the x, and I want to revolve that around the x-axis, what I'm going to do is I'm going to get something like this v here. And as this goes up, this is going to spin around. Now what I didn't do, and I meant to do this here, is actually give you a bounds of integration. So let me do that now. This is going to go all the way out to 5. So you're going to go from 0 to 5 here. This is obviously going from 0 to e to the 5. So e to the 5 is a rather large number. But anyway, so when we do this idea, we can no longer use the standard techniques or the classical techniques from geometry. We have to use the calculus-based techniques, which are not that complicated, but we need to revisit them. So what we need to do is we need to identify those bounds. So we have 5 on one side, so we need to find the other bound. It looks like that bound is, well, that doesn't make any sense, right? E to the x goes through 1. So we're going to have to make a little adjustment to this problem. We're going to have to call that e to the x minus 1, which is fine. E to the x minus 1 is fine. And so we're going to go from 0 to 5 here. And that's going to, this is going to pinch to be 0, and it's going to kind of flare out like a horn, which is an interesting concept there. But let's go ahead and get to the calculus piece. We would say then that our volume is from 0 to 5 pi e to the x minus 1 squared dx. Okay? Now, we could square this. We could do this with that. I would, again, use substitution like we did in the previous example. I would say u is e to the x minus 1. Du is e to the x dx. Now, as I say that, that's probably a really bad idea. And I could start over. I could say, okay, well, I'm going to throw away this video. But I want to show you that sometimes you think to yourself, okay, this is very simple. You just do a substitution and you're done. And in this case, I think it's going to turn out a lot more complicated if we try to do it that way. So we're not going to do it that way. We're going to, we're just not going to do it that way. So we're going to completely eliminate that path, and we're going to do it the standard way. So get rid of that, and we're just going to write this all the way through. We're just going to say v is 0 to 5 pi. Now if I multiply this out, I can use the FOIL method. So I get e to the x times e to the x is e to the 2x. E to the x times negative 1 is negative e to the x. Negative 1 times e to the x is also negative e to the x. So I get negative 2 e to the x. And negative 1 times negative 1 is a positive 1. So from there, what I can do is I can take the antiderivative of each one of these. That tells me that v is in, we have this pi in front. Antiderivative of e to the 2x is 1/2 e to the 2x. The antiderivative of e to the x is just e to the x. So we have that negative 2 coefficient. And then the antiderivative of 1 is x. And this is going from 0 to 5. So at this point, we just simply need to plug in the values for the lower and upper bounds, respectively. We can say v, plug in the case where x is 5, we say that's 1/2 e to the 10 minus 2 e to the 5 plus 5. And then we subtract. That's the case where x is 5. We need to now put in the case where x is 0. So that's 1/2. Well, e to the 0 is just 1. So that's 1/2. Again, e to the 0 is just 1. And of course that is just 0, right? Plug in 0 for x is 0. So I have this. I can continue on. I can take the pi out. And now I have 1/2 e to the 10 minus 2 e to the 5. And now I have a 5 here minus a half plus 2, right? And so I do plus 5 minus a half plus 2. So V is 1/2 e to the 10 minus 2 e to the 5. So that would be 7 minus a half, or 14 halves minus a half, so 13 halves. It's not a super pretty answer, but it doesn't mean it's not the right answer. It just means it's not super pretty. And so, again, this was an example of where trying to be clever with substitution was a bad idea. Sometimes it is just useful to just crank it out straight. And hopefully you're getting a little more comfortable with the DISC method. And we're going to start getting a little more complicated in the next few videos.